Hi everyone, my name is Xiaofei. Today I'm going to introduce you about our work on how machine learning can support scientific discovery learning for K-12 STEM education. Nowadays, scientists are using machine learning to suggest novel correlations, accelerate the data search process, and review complex patterns. However, little research effort has been spent on preparing K-12 students for such a rapid trend of data-driven and machine learning-powered scientific discovery. With already tight school curriculum and lack of teaching resources, how can we better integrate machine learning into K-12 STEM learning? For K-12 STEM education, scientific discovery learning is a common pedagogy approach. It involves ask scientific questions, generate hypotheses, explore data, interpret patterns, and has such natural connections with machine learning. But without certain data and machine learning literacy, it's challenging for K-12 students to learn machine learning and make sense of results generated by machine learning. For example, here is a pair plot visualizing clustering result on a dataset about heart disease and related healthcare factors. If we ask kids to interpret potential risk factors to have heart disease from the graph, they can easily get lost with such intimidating graphs, with so many data attributes displayed separately and overwhelming numbers. Instead, let's look at the visualization here. At the very first glance, kids can recognize that there are two clusters generated. Similar faces are grouped together. Then, during the science talk, they can easily verbalize that the upper cluster is a group of friendly smiling faces with small eyes, while the lower cluster shares bigger eyes and looks shocked and surprised. We can also provide such overlay view by stacking all the faces from the group on each other to support more efficient recognition of group patterns. How to generate these faces? What we are doing here is utilizing a data visualization method named face glyph to visualize multidimensional dataset by translating each data attribute to individual facial features. For example, here heart disease or not is translated to the curvature of the mouth, so no heart disease is mapped to such a smiling mouth, and have heart disease is mapped to such an unhappy mouth. And the eye radius is mapped to the value of smoking history in individual data points. The slant and the vertical position of eyebrows are mapped to the values of age and BMI respectively. With these data patterns, kids can be further scaffolded to make sense of the patterns in scientific context and generate hypotheses based on data. For example, by comparing these two clusters, they can hypothesize that having heart disease or not seems to be related to smoking history and age, but not that relevant to BMI value, and there is such a big variation in BMI within the second cluster. Previously, to study how K-12 teachers apply machine learning components to scientific discovery learning activities for different STEM subjects, we have conducted a small-scale co-design workshop study with in-service K-12 STEM teachers. We provided a list of machine learning components related to K-means clustering, including data mapping, similarity computation, manual clustering, and automatic clustering. And we guided teachers to create scientific discovery learning activities that involve orientation and initial hypothesis generation, initial investigation, and further investigation plus hypothesis update. From the 4-teacher design lesson plans, we extracted a list of machine learning scientific discovery connections on how they can be used to support specific scientific discovery learning behaviors. This is the frequencies of them being applied by teachers in their own design. However, at that initial stage, the data is from K-12 teachers rather than students. Also, the connections are collected from conceptual design rather than authentic learning behaviors happen during the machine learning-empowered scientific discovery. Therefore, in this study, we invited 25 high school students. We collected and annotated video and audio recordings of their process of applying machine learning to investigate data. We conducted preliminary analysis on how different machine learning components are associated with different scientific discovery behaviors. We also conducted linguistic analysis to analyze the cognitive complexity during the process. And this time we focus on the scientific investigation part within a scientific discovery learning procedure. This part involves learning behaviors including observation and orientation, exploration and experimentation, data analysis, pattern interpretation, and reflection. The major machine learning components include getting familiar with the interface through constructing their own faceglyph, interpret the classification results by applying the machine learning component similarity computation, analyzing centroid generated by different groups of data points, analyze outlier from clusters, select k-values for k-means clustering, and conduct cluster analysis. The results show that machine learning components are associated with different scientific discovery behaviors. In our research, we discovered that the cognitive process scores were higher during the later stages, such as reflection and analysis, and lower during the earlier stages. This indicates that the integration of new machine learning components did not make the cognitive difficulty of initial interaction higher than data analysis and pattern interpretation. We also observed that despite being a more complex task that requires a blend of machine learning components, cluster analysis presents a lower level cognitive complexity in comparison to k-value evaluation and intra-group variation comparison. This could be attributed to that we unveil the complexity gradually by placing cluster analysis in the end when learners have already equipped with other machine learning components that is part of the cluster analysis. This indicates the need for further improvements in visualization and interaction design to support the analysis of variations among different attributes within a group of data points, as well as the evaluation of overall clustering results. For our future plan, we would like to jointly model the visual features, textual features, and the involvement of different machine learning components to investigate the scientific discovery learning activities. And also, we're considering incorporate the temporal patterns by applying long short-term memory model. Thank you for listening. Please feel free to contact us if you have any questions.